It's the physics video lecture. Physics 105A video lecture 31. And we're talking about the two-body problem, the Kepler problem. So what is that all about? Last time we reduced the two-body problem to a one-body problem. And I'll just remind us of what we did. We had an M1, M2, right? They both have their location. But we constructed a difference vector named R, and we were able to express these two positions in terms of R, if we took the origin as the center of mass, which I draw there with a little star. So here's what we ended up with. R second derivative is equal to, and we're doing a central force, so we said we have F of R times a unit vector. Okay, so that defines a central force right there. Now, we can just take this formally as a mass times an acceleration equals a force, but in the context of the two bodies there, we have this M being the reduced mass, so we could call this reduction of two-body problem to a one-body problem. And we have everything else, for example, under this formalism, we have a potential energy like this. We have energy conservation, 1/2 m r dot squared plus u equals e. And we also have angular momentum conservation. And I'm going to go to a lowercase l. We were doing uppercase last time. L equals r cross m r dot was conserved. From there, we were able to argue that motion is restricted to a plane, and therefore we went to plane polar coordinates. I'll fit this all on one board here. So motion restricted to a plane. Therefore, we go ahead and let vector r equal r hat. Oh, that's right, just like that. So plane polar coordinates, and then r dot would be r dot r hat plus r phi dot phi hat, right? Plane polar coordinates. So that was the reduction of two-body problem to a one-body central force problem. And let me go ahead and write that down. Is the reduction of the two-body problem to one body, formally, right? And of course we can calculate, we can solve for R, and then we can go back and get these R1s and R2s. Okay, so what about the Kepler problem? So that's our goal, is to do the so-called Kepler problem, which is the two-body problem. I'm going to write that here and then talk a bit about Kepler and Kepler's laws of planetary orbits. Kepler problem. So the two-body problem is often referred to as the Kepler problem when you're using Newton's law of universal gravitation. So let's talk a bit about Kepler's contribution. So, and you should look up some articles on Kepler, very interesting, but for our purposes, he was able to obtain, just really by geometric means, the 3 laws named after him, laws of planetary orbits. So that's what I'm going to discuss here, Kepler's laws of planetary orbits. What we want to do is discuss those, and then we'll see how Isaac Newton used his knowledge of Kepler's laws to obtain the law of gravitation, which he then generalized and was able to then prove all of these laws based on this formalism up here, as well as going far beyond just the planetary orbits, right, to just universal behavior under the gravitational force. So Kepler's laws of planetary orbits were obtained, like I said, just by analyzing astronomical data. These mechanical concepts had not yet been invented. Okay. Galileo was just barely starting his mechanics, projectile motion and stuff. Newton was not yet born. Okay. So what are these laws of planetary orbits? The first one is about the shape of the orbit and with regards to the sun. So the first law is that the orbits of the planets around the sun are ellipses. Okay. Planets around the sun are ellipses. They're ellipses and the sun is at one focus. So I'm going to do a little description of this. So with the sun at one focus. Okay, so that's the first law. And at the time, he first learned it for Mars, and then I think eventually, Venus, Earth, Mars, out to Jupiter, I suppose. Okay. First with Mars, but then with the planets that were known at that time. Ellipses with the sun at one focus. So what is an ellipse? Well, let's actually start with what is a circle, and then we'll graduate to ellipses. So a circle we can get by taking a central point here, and a set of points equidistant from the center of the circle. So you just construct it with a string and a pen. It's always fun. Once more with feeling. This thing's pretty generous here. Okay. Good. There's our circle. And of course our circle has a radius r, and that's the center of the circle. And we could have circular orbits as well. The circle is a limiting case of the ellipse. So yeah, just for completeness, I drew the circle. But now let's do the ellipse. Okay, so to construct an ellipse, we need its definition as the set of points where the sum of distances from 2 points is constant. And the loop of string will be good to have. Let's go ahead and construct an ellipse and label it with some relevant characteristics. So the ellipse, there's our circle. Go ahead and draw the ellipse. Yeah, so the construction principle is is obtained with these 2 points. I'll put them, these are the foci of the ellipse. I'll put them a fair distance apart. If you put them, and I'm just going to construct it by doing the same construction except with the loop around these 2 points, because the sum of the distances from these 2 foci to a given point is unchanged if I use this loop here. In the limit of pushing these foci together, then I have a circle. Okay. So we'll go ahead and set them apart a fair amount. Even though I'll even note right now the planetary orbits, if we were to draw them, would hardly be indistinguishable from a circle. The foci are pretty close together. Good, but here's the ellipse, and we're going to label it. Okay, so let's give this a try here. Beautiful curve. Okay. So there's the construction principle. Again, compared to our planetary orbits, very exaggerated. Comet orbits, however, work like this. So, good. Let's locate these foci here and here. Those are the 2 foci of the ellipse. And what did we say? The sun is at one of these foci, and this other one here is a mystery spot. In fact, in a different mathematical presentation, it won't even be present. So the sun, we'll go ahead and say the sun is right here, and there's nothing here. Okay, nothing at that one. We'll take that being location of the sun. Let me write that a bit to the side. I'll label that in a moment. Okay, so what characterizes this ellipse is its semi-major and semi-minor axis. So we say that what I'm going to do is put this, here's what I'm going to do. I'm going to put a coordinate system here. I'm going to put 2 coordinate systems, but we'll start with a regular XY coordinate system. Here we're going to put the origin right at the geometric center of the ellipse. So we'll go ahead and call this X and this Y. Okay. And then we can define the extent of this ellipse. Right? It has a long and a short aspect. And this here is 2 times A, where A is called the semi-major axis. And this here is 2 times B, to B. Okay, so B is the semi-minor axis, and A is the semi-major axis. Major axis. Okay, so there's the construction, and I'll just write here focus. And here's a focus. So in terms of a planetary orbit, we would have, say, the sun right here and a planet out here on the ellipse orbiting. Now, in this coordinate system, we have the equation of the ellipse, where we have x squared divided by a squared plus y squared divided by b squared is equal to 1. Okay. Now there's another way to look at this ellipse, and maybe we'll use a different color. So suppose we call this the x-axis, okay, but we're going to put a y-axis parallel here. So this second axis, or this second coordinate system is going to share this x-axis, but it puts the origin at the focus. So this is the one kind of ellipse. Second kind of ellipse, also ellipse, origin at one focus. This here we would say the origin at the center, at the geometrical center. I'll just call it, say at the center, right, of the figure. So now we have the origin at one focus, and then if we take a point, I'll go ahead and go red out to here, and I'll call that R, so that the distance from this focus to a point on the curve is R, okay? So if we have the origin at one focus, we can write what's called the polar form. There's a R and there's an angle phi. So you can see phi will go from 0 to 2 pi, and the 0 angle is going to be here at the positive x-axis, which is shared, right? These are both x-axes. So yeah, what's the polar form of the ellipse? Polar form, we would say R is equal to P divided by 1 plus E cosine of phi. Okay. So the box around both of these. P is called the parameter, E is the eccentricity, and we can relate P and E to A and B. In fact, we will do that later on. I'll leave it unstated now. Eventually, these are going to be filled with physical content from Newton's law. But for the moment, this is just the geometric description. R is equal to P over 1 plus E cos phi. And just so you see what's going on here, P is constant. All right, P is a constant, positive constant. E constant. And you can see that when E is equal to 0, R is equal to P is equal to constant, we have a circle. Okay. Note E, let's write that E equals 0 if E equals 0, then we have a circle. And you can also see that P over 1 plus E, when phi is equal to 0, that's that distance right there. And P over 1 minus E, when phi is equal to pi, puts you over at this left end. So you can relate P and E to A and B, and we will do that in due time. Good, so we have the polar form, which then you notice the polar form doesn't know anything about the second focus, right? Origin at one focus. Okay, let's send that up. So there's, back to Kepler's laws, orbits of the planets around the sun are ellipses with the sun at one focus, and we have all the necessary definitions here for what is to come. Good. So what's the second law? I'll go ahead and erase all of this. Kepler's second law, it's the law of, oh yeah, for the first law we should have written law of orbits, just to remember. So first law, I'll go ahead and put this here, was the law of orbits. And then the second one would be the law of areas. Way to remember, you got the orbits, now you got the areas. And this second law states that the radius vector, namely this point that goes from the focus to our orbiting body, this radius vector sweeps out equal areas in equal times. The sun, planet, so sun to planet radius vector sweeps out equal areas in equal times. I can do a crude drawing of that. I'm not going to mess that one up in equal times. So for a nicely elongated ellipse like that one right there, what you're saying is that this side of the orbit here, right, the radius vector is going to sweep out this area, and the time it takes to sweep out that area is the time it takes to sweep out an equivalent area, say on the other side of the orbit. So I'll draw a really thin one. So these are equal areas. Of course, what that means is that our planet is orbiting much slower on this side, moving faster on this side. Okay. So faster the closer to the central body. Let's put a central body here. And there's our planet orbiting. So equal areas in equal times. And everywhere along here as well. It's interesting though, Kepler's data, after all, his orbits were pretty close to circular. And so what he was calculating and figuring out was by no means, as dramatic as this, okay, as drastic as that. Good, so that's the equal areas and equal times. And the third law is the law of periods. And we're talking about the time it takes for a complete revolution. So let t equal the time of revolution, i.e. period of the orbit, and at the time at the point where he had his law of periods, he had a whole collection of these planets now. It wasn't just Mars. So this is the one that he found last. And what he found was that for the entire system of planets orbiting Earth, or the system of not orbiting Earth, sorry, planets orbiting the sun. Somebody correct that. Good. For the system of planets orbiting our sun, you would take the period squared divided by the semi-major axis cubed. Okay. Period of orbit squared divided by the semi-major axis cubed was a constant. So one and the same constant. In other words, if you took the Earth period divided by the Earth's semi-major axis, squared and cubed, you get this number. Do the same thing for Mars, the same number. Jupiter, the same number. Okay. And yeah, and we often say t squared proportional a cubed, right? And we talked about this earlier in the semester in the context of an interesting problem, mathematical problem that we did. Yeah, so this is the same constant for the entire solar system. For example, if you were to choose the unit of time as being 1 Earth year, time it takes Earth to orbit the sun, and if you took the unit of length as Earth's semi-major axis, okay, then this constant would be equal to 1. Okay. And then the other planets with their different periods and semi-major axes would all, in terms of Earth orbits, would also be constant equal to 1. So for example, I think Jupiter's orbit is 12 Earth years, and so suppose, let's just say it is 12, you could look it up. Then you'd have 144 here, and then you'd have to have the the multiple of the Earth-Sun distance cubed would give you those 144, okay? That's just an aside. Main thing is there's a constant there, period squared over semi-major axis cubed. So those are Kepler's 3 laws. We are going to prove them. We're going to demonstrate them for the two-body problem once we have Newton's theory of gravity. So in the board that I erased a while ago, with the force law, we have to have Newton's law of gravity for that force law. And then we're going to prove all 3 of these laws. And the form in which we prove them shows them to be much, much more general, because we're not tied down to the Earth and the planets and the sun. The same thing can be applied to Jupiter and its moons. So any central body problem, and Newton already did this, by the way, he applied the whole results of his analysis to the various planets and their moons. Good. Let me consult the clock. Okay, so what I have next in mind is to run through the arguments that were available to Newton. So Isaac Newton used the knowledge of Kepler's laws to derive or to obtain somehow his law of gravity. So that's our next topic. Gotta erase this, send this up here. So the next topic is, how did Newton discover his law of gravity? That's what we're going to do here. Okay, so next, how did Newton obtain, let's call it the gravitational force law? Question mark. Yeah. So yeah, how about the sitting under the tree here with the apple? That's the story. Good luck drawing Newton, big wig, reading a book. Okay. So there's actually some significance here beyond the humorous part. There's a moon out here as well in our story. Okay, we can color it moon, maybe the apple. Okay, the idea that I'm going to present here is the following. The significance of an apple and a moon in the picture is the idea that both apple and moon are obeying the same law, right? The same law of gravity holds for the apple and holds for the moon. Before Newton, these were completely different things. Now, these Kepler's laws were not dynamically based at all. It was empirical and geometrical. So in the meantime, dynamics has been invented. So the first point here is we're going to say the same force acts on, or the same type of force, apple and moon. Okay. So that's the big revolutionary breakthrough. The second point is for the apple, we're talking projectile motion. Right? We're talking F is equal to mg. Okay. Now, if the same type of force is acting on the moon as on the apple, then by the, I mean, let me write here law of free fall. Okay. Law of free fall, right? Mg, free fall. Okay. Now the next argument is, you can, instead of the apple, you can talk about Earth and Moon, and if you're talking about the Earth and the Moon, then you could say, well, the force that the Earth exerts on the Moon is going to be proportional to the mass of the Moon. So let's go ahead and do this. Capital M, little m. This time it's the Earth and the Moon. Okay. So by the same argument as up here, we're going to have force. I'll write force, let's say, let's be explicit about this. Force on the Moon F is proportional to the mass of the Moon, just like up here, mass of the apple, mass of the Moon. And then, because of that, by Newton's third law of motion, this is really important. By Newton's third law, then the force on Earth due to the Moon has to be proportional to capital M. So by Newton's third law, the force is also proportional to capital M, which means it's proportional to the product of the two masses, okay? So for two interacting masses, I'm not going to put an equal sign yet, we just have the proportionality M times M. Okay, yeah, so this picture is important here. We're talking about the Earth-Moon system now. Strictly speaking, it could be the apple acting on the Earth as well. But let's go to the Earth-Moon system. So this here, due to the law of, same as the law of free fall, and turning it around here is just by Newton's third law. You know, equal and opposite, right? You have force like that, you have force like that. Okay, so that's what we have so far. The force is going to be proportional to the product of the two interacting masses. Now the third point, or actually the fourth point I'm going to make here, it's going to be good. I'm going to leave this law up here because we're going to make use of that. So points 1, 2, 3, so I'm extending here point 4. Consider now a circular orbit. Okay, so we have a circular orbit, and we'll go ahead and put the central body here, capital M, and the smaller one, lowercase m. Okay, that's a perfect circle right there. And there's the radius vector r from the center to the mass there. So we're considering a circular orbit. Now we have mass times acceleration is force, right? Newton's law of motion. It's a circular orbit, so that's mv squared over r is equal to f. Okay. So what we're going to do now is analyze this. That's why I'm just going to turn this around. So f is mv squared over r. So we've got the m there. Now, and we'll actually divide by r. So the v is 2 pi r divided by t, right? So that's the circumference divided by the period. That's the speed for a circular orbit. We square that, and maybe a little more room here. Actually, I'm about to make use of this, but I'm going to erase it. So let's see what we have so far. We have 4 pi squared m, but we have r squared in the numerator and r t squared in the denominator. Now here's where I'm going to use Kepler's third law, and where Newton used Kepler's third law, because we know that t squared is proportional to r cubed, because we're doing circular orbits, right? Semi-major axis is just the radius of a circular orbit. So continuing here, I'm getting rid of the equal sign because I just have a proportionality here now, so I can ditch the 4 pi squared m. What I have here is r squared over r times r cubed. Using Kepler's third law, equals 1 over r squared over r to the fourth, 1 over r squared. So that's where the celebrated inverse square law comes from. I'll give that a few exclamation points, okay? So yeah, we can complete this with saying the following. So F gravity is postulated to be proportional to the product of 2 masses. I'm going to go back to m1, m2 over r squared. The proportionality constant has to be measured, and can be measured as well. It was measured by Cavendish for the first time in laboratory conditions. So F is equal to G m1, m2 over r squared. G is, I think, 6.67 and minus 11. With the units, Newton meters squared per kilogram squared. Look this up, I should know this, but yeah. The point is, this is just obtained under laboratory conditions. Very interesting experiment, of course. So it's right here, Cavendish. But that's in the future. Newton does not yet have the value of its proportionality constant. Okay. So that's where the idea for this. Now the proof is to take this law back into our formalism and obtain all of Kepler's laws and then some. Okay. But yeah, this is where it comes from. I'm also going to say we just used the circular orbit. Once we have the whole formalism in place, we can actually prove that an elliptical orbit will actually give us the very same thing, 1 over r squared. So we can prove that rigorously for ellipses, but right here, that's a simple argument just using circles. Okay. And I'm sure that Newton used the circle first, simply because it's the easiest way. Okay, let's consult the clock. Yeah, this is a good spot, I think, to finish for today. I should have put some more words. I said some words, you guys put some words in here. So this is the result of this idea here. And here's where we plugged in Kepler's third law and then obtained the 1 over r squared dependence. We already had the product of the masses, so we put that in the numerator. And Newton does not yet have the proportionality constant. That can be measured. That can literally be measured by, under very careful conditions in the laboratory, having steel lead balls or what have you, be attracted to each other, and you measure that with, say, a torsion balance or something. But good, we'll get there next time. So what are we doing next? Actually, now that we have this, we're going to go back into the formalism, the central force formalism, A number of things to do before we make use of this, but that'll all happen next time. Okay, good. See you guys then.